Okay, we're still in 10.1 in Barnett, and now we take a look at one-sided limits. So we write the limit as x approaches c from the left. This little negative here means from the left. Okay, little negative written like this means from the left of this function. Okay, so we write the limit as x approaches c from the left of f of x to equal k, and call k the limit from the left, or the left-hand limit, if f of x is close to k whenever x is close to c, but to the left of c on the real number line. Okay, and likewise we write the limit as x approaches c from the right, by writing this little plus here that indicates from the right, of f of x to equal L. Well, we call L the limit from the right, as you could imagine, or the right-hand limit, if the function is close to that value L whenever x is close to c, but to the right of c on the real number line. In order for a limit to exist, the limit from the left and the limit from the right must exist and be equal. This is an important statement that's given a lot of attention in your textbook, and you should go over this to make sure you understand why that's the case. Okay, we're going to look at an example here, and let's make sure we understand these two. So here's some function f of x given by this piecewise graph, and let's see. So in blue is the function values, and let's take a look at the left-hand side of the screen here. It says the limit as x approaches 2, here's 2, from the left of f of x is equal to 2. So notice the minus means go left to right, right? The limit from the left means go left to right. As I trace my graph left to right, and I get closer and closer to x equals to 2, I notice that the function outputs are getting closer and closer to 2. So the answer is 2. On the other hand, if I say the limit as x approaches 2 from the right of f of x, well, this plus means go from right to left. So trace out the functions from right to left, and look at what's happening as you're approaching x equals to 2 from right to left. Well, we're getting closer and closer to the value 5. Now notice, there is an open circle here. The function itself at 2 is not defined to be 5. But that's okay. You're not interested in what happens at 2. You're interested in what's happening just to the right of 2, near 2. Okay? So once again, you're interested in what's happening near 2, and in this case, because we have the plus symbol, we're interested in what's happening near 2 to the right of it. And to the right of it, the function is approaching 5. That's why this limit is 5. Now notice, since these two are not the same, in other words, the limit from the left is not the same as the limit from the right, these two are not equal, then the limit does not exist at 2. So the limit as x approaches 2 of f of x, right, not from the left or from the right, just as it approaches 2, does not exist. Okay, that's what we would write. It does not exist at 2. Now on the other hand, if you look at another example with the same graph, look at what happens as the limit as x approaches 0 from the left. Once again, from the left means you're going left to right. Okay, going left to right, tracing out our function, as x gets closer and closer to 0, here is 0, we're getting closer and closer to 2, so the limit is 2. Likewise, the limit as x approaches 0 from the right means right to left, of our function, well, when we go right to left, as we approach 0, we're also getting closer and closer to 2. So the limit must be 2. Well, since the limit from the left and the limit from the right both exist, and they're both equal to the same value, in this case 2, then we say the limit exists at x equal to 0, and we write the limit as x approaches 0 of f of x equals to 2. So that's a good example of how to find the limits visually, reading them off of a graph. Okay, you saw how to do it for one-sided limits, and how that helps you do it for the limit at that point. Why don't we take a look next at some limit properties? Okay, so assume f and g to be two functions here that have the following two limits, which exist and are finite. The limit as x approaches c of the function f is L, and the limit as x approaches c of the function g is m. Okay, then one property is that the limit of a constant is the constant. In other words, if you have the limit as x approaches c of some constant a, then that is always going to be a itself. This is really easy to see. Think of just graphing some constant a. The graph of that is just a horizontal line, right? It's like saying the limit as x approaches z of 5, the function 5. Well, that's the constant function. No matter where you are, as you approach from the left to the right of this value c, the limit is always going to be a, because that's the point c, comma a. The second property is the limit of x as x approaches c is c. Well, likewise, reasoned the same way, if you draw a graph of this, the limit of x is simply the line y equals to x, right? That's the limit of x. As x approaches c here, what do we know? That this point has coordinates c, comma c. Okay? So since it's y equals to x, anywhere you pick your c, maybe I pick it here, this is c2, then the limit would be c2, because the function is y equals to x. Another property that we have is that the limit of the sum of the functions is equal to the sum of the limits. This is always abbreviated. The limit of the sum is the sum of the limits. So what that means is that if you have the limit as x approaches c of f of x plus g of x, you're adding these two functions, well then that's equivalent to saying the limit as x approaches c of f of x plus the limit as x approaches c of g of x. In our case, this would be L plus M, right? Because the limit of f is L and the limit of g is M. Okay? These are explaining your textbook with a little more detail if you'd like to look at that. Well, the same thing holds for the difference of a function. So if you have the limit as x approaches c of f of x minus g of x, that's the same as the limit as x approaches c of f of x minus the limit as x approaches c of g of x. Okay? So in that case, this will be L minus M. Let's take a look at a few more properties here. The limit of a constant times a function is equal to the constant times the limit of the function. So if you had something like the limit as x approaches c of some constant, let's call it k, times your function f of x, right? That's what you're taking the limit of. Well, that's the same as multiplying k by the limit of your function as x approaches c. So you could rewrite it this way. That's a helpful property that will come into play later on when we do derivatives. Likewise, the limit of the product of the functions is the product of the limits of the functions. So if you have the limit as x approaches c of, let's say, f multiplied by g, then we could say this is the same as the limit as x approaches c of f times the limit as x approaches c of g. So in this case, this would be L times M. Okay? The same thing holds for the quotient, as long as you remember that the denominator can be 0. In other words, the limit of the quotient is equivalent to the quotient of the limits. Here is what I mean. If you have the quotient now, f of x over g of x, this is the same as the limit of f of x as x approaches c over the limit as x approaches c of g of x, provided that this bottom one is not 0. And finally, you have the limit of the nth root of a function. So if you're taking the limit as x approaches c of the nth root of some function, f of x, well, this turns out to be the same as the nth root of the limit of that function. Okay, which you can write this way. So those are the limits, the limit properties.